To watch these important lessons, subscribe to DP Education's YouTube channel right now. Click on the bell icon to stay updated on the latest lessons. Sri Lanka's largest free online school, DP Education.
Hello my dear students, welcome to today's lesson. Today I am going to continue with the lesson Electromagnetism and Electromagnetic Induction. Now in the previous chapter, you all were able to understand that when a current flows through a conductor, there is a magnetic field induced. To identify the direction of the magnetic field depending on the direction of the current flow, we used two rules. One is the Maxwell corkscrew rule and the other one was the right hand grip rule. So with all the activities, you all were able to understand that. Moving on from there, now we will try to understand if there is a magnetic field already present. You have a magnet. Between the fields of the magnet, you place a conductor that can carry current, and while the current is flowing through a conductor kept across the magnetic field, will there be a force acting on it or not? If there is a force, what would be the direction of the force? That is what we are trying to understand here. To do that, we will discuss an activity first. Force acting on a current carrying conductor placed in a magnetic field. So the activity, find out whether a force acts on a current carrying conductor placed in a magnetic field. So to do that, these are the apparatus that we need. We need a U magnet, a cardboard piece, like a rectangle shaped piece of cardboard so that we can fix the connecting wires and the conductor. Then a conducting rod, or you can say a conductor, a straight conductor, and then we need batteries. Now I will explain the method in the next slide. These are the materials needed. We need a U-shaped magnet, a piece of cardboard, a conducting rod that can move independently. Not the connecting wires, we need the conducting rods and the batteries, and also we need connecting wires. So this should be a rod that can move freely because we are going to observe whether a force acts on this conducting rod. Is that clear? So then we'll discuss the method. Here you can see the method. I will explain it using the diagram first. Now here you can see, students, we have the U magnet. Now you have seen the U magnets. North is on top, the south pole is at the bottom. So we place the U magnet so that the north pole is up and the south is below. At that instance, if you look at the direction of the magnetic field, you know it is going to be downwards because from north to south. So you have the magnet like that. The direction of the magnetic field lines will be from top to bottom, downwards. Is that clear? Then what we do is, we have this piece of thick cardboard piece there. You make two holes there and you connect the connecting wires. Now this is labeled as point A, here it is point D, and then you can see the batteries there. Now according to this diagram, you can see the positive terminal is there. So then we have a switch, the switch is open now. Then you can see brass rods. We need brass rods. So in the diagram I only marked as conducting rods. So here we will be needing two brass rods that are connected, inserted into this cardboard so that it will not move, and the other end of the brass rods are placed on this magnet. Now you all know brass is not attracted to the magnet. You can remember that. Brass rods not attracted to magnets. or they are not magnetic material. That is why we use brass rod. So here I will say conducting rod. Now connecting wires. In addition to that, we need 2 brass rods. Is that clear? Then here you can see another rod BC. This is also a conducting rod. Now that is also going to be a brass rod. Now we need 3 brass rods. Now these 2 are the blue color ones are connected. They cannot move. One end is fixed to the board, cardboard, and the other end is kept on the U magnet. So they cannot move. But this particular conductor BC, you can see it's free to move. But it is also a conductor. So when we close the switch, you can see the circuit will be complete. Why? The current will start flowing from here A to B. Since the BC rod is kept on BC, then from C to D, and the circuit is complete. So that way the current can flow. Since the BC rod is in contact with the brass rods, the current can flow continuously. So this is what we will do. We will make the setup this way. Then when you close the switch, you can see the direction of the current flow. A to B, then B to C, and C to D. That way the current will flow. At that instance, you have to observe what happens to this particular BC rod. Whether it moves or not, and if it moves, in which direction. Whether it's towards the magnet or away from the magnet. That is what you need to observe first. Then what we do is we open the switch and then we change the terminals of the battery so that the positive charge comes to the other side. Then of course, when you close the switch, the direction of the current flow will be different. In the second instance, current will flow from D, C, B to A because the terminals will be changed. Is that clear? So in the second instance also, we will close the switch and observe the conductor BC. Whether it moves and if it moves, in what direction. Towards the magnet or away from the magnet. After that, what we will do is, we will repeat the activity by changing the poles of the magnet. You will have the south pole up and north pole down. So the magnetic field lines will act in the opposite direction. So we will be changing the battery, terminals of the battery, and also we will be changing the direction of magnetic field. So 4 instances. Again, after changing the magnetic field also, we do the same thing. We have the batteries this way. So the current can flow from A, B, C to D. Then with the same way, where you have the south on top, north below, again you change the terminals of the battery. So the current flows from D, C, B, A. So 4 different instances. In all the instances, when you close the switch, you have to observe this rod BC. Whether it moves and if it does, in which direction. That is what you need to observe. So if the rod moves, what can you understand from there? Now, if an object at rest has to move, there should be a force acting on it, unbalanced force. So if the rod moves, you know there is a force acting on the rod. So how did we get that force? Because of the current flowing through a conductor placed in a magnetic field. So if there is movement, you will know that there is force generated. And if there is force generated, you will have to observe the direction of the force. How do we do that? The direction of the movement of this rod BC will give you the direction of the force. So that is what you need to observe. You have to look at the rod BC under 4 different instances. Changing the terminals of the battery, changing the poles of the magnetic field or the direction of the magnetic field. Is that clear, student? So we will look at the steps. Place the U magnet on a table and place the 2 brass rods as shown in the figure by inserting them through 2 holes pierced in the thick cardboard. Connect the 2 dry cells and the switch S to the ends A and D of the brass rods. Next, place the conductor BC on the 2 brass rods between the north and the south poles of the magnet. So, place the conductor BC on the 2 brass rods between the north and south poles of the magnet. That is part of the activity. I'll move on to the next slide where I discuss the rest of the steps. So, here you can see. Allow a current to flow by closing the switch S. Then a current flows from the cells through the brass rods along the direction AB and through the conductor in the direction BC and reaches the cell from the direction CD. So, in the conductor, the direction is BC. Like I said, ABCD direction. So, here it is going to be ABCD direction. Is that clear? Observe the conductor BC when the current flows. Now, repeat the above step by changing the cell terminal to change the direction of the current flow. So, here the direction of the current flow is going to be DCBA. Now, observe the conductor BC. Then, repeat the above step after changing the top and bottom poles of the magnet. Now, observe the conductor BC. So, like I said, 4 different instances. We are changing the direction of the current flow. 2 directions ABCD, DCBA when the north pole is up and south pole is down. Then we change the poles of the magnet, south pole up, north pole down. So, the magnetic field is upwards. Then also you have the direction of the current flow ABCD and DCBA. So, 4 different instances. I am sure you all can understand the activity. So, let's go to the lab and do the activity now. Okay, students. So, now I am going to do this activity in order to observe whether a force acts on a current carrying conductor placed in a magnetic field. So, to do this activity, I have all these materials connected as a circuit. Now, here you can see these are 2 dry cells connected together. You can see this is the positive terminal of the dry cell and here it is the negative terminal of the dry cell. So, positive, negative. So, if we close the switch, now here you can see I have connected a switch, but at the moment the switch is open. So, then I have this setup here where I have the magnet. It is in the shape of a U magnet. Here, of course, it is a magnet where we have the north pole on top and the south pole at the bottom. For you all to identify it easily, I have used labels here. This is north and south at the bottom. Then here you can see this end where there are 2 rods connected. And this end of the rod, this first rod here, it is a conducting rod that is labeled as A. And the second rod, this end, I have labeled it as D. So, this is a wooden frame that is used to connect the 2 rods. Then here you can see this is a brass conductor which I have labeled as B and C on top. So, here you can see B and C. Now, when I place it this way, the order will be A, B, C, D. So that is how we are going to use the setup. So as you can see, this is a conductor. I will place it in the between the magnetic field. So the north pole, the south pole of the magnets, the two ends of the magnets, and here we have the conductor placed between the magnetic field. And when I close the switch, there will be a current flowing. So we are trying to observe whether there will be a force acting on a conductor through which a current flows, and the conductor has to be placed within a magnetic field. So here is the magnetic field, the conductor is there. When I close the switch, what will happen? From the positive terminal, current will flow this way to point A of this rod. And then since this conducting brass rod is in contact, from point B to point C of the brass rod, and then the fixed rod here from C to D here. Although the label is put in C there, you all have to remember, students, the contact point is here. So this is just for the identification purpose. I'm sure you all know that the current flows through the complete circuit. So the contact points are here, but just to identify the direction of the current flow, I have labeled the points A, B, C, D. So now since the positive terminal is here, from the positive terminal, current will flow from A to B. Then in this brass rod, the piece of brass rod, current flow will be from B to C. And then through this rod, C to D and back to the dry cell. So remember, the current flow will be A, B, C, D, that direction. And north is on top, south is below. So those are the things you have to remember. So when I close the switch, look at this brass conductor carefully. You have to observe whether it rotates or moves, or if it moves, to which direction. Whether it moves away from the magnet or towards into the magnet. Those are the things you have to observe, students. So I'll place the rod properly. So now I'm going to close the switch. Observe what happened. Did you all see? I will repeat it again. Bringing the rod back to the initial position. I'll close the switch. Now can you see? I'll just rotate it so that you can see the letters at the position. Now A, B, C, D, still it is the same. Earlier the rod was here. Now it has moved away from the magnet. Once more I will do that. Again I am going to repeat it. So here you can see current flow A, B, C, D, north on top, south below. When we close the switch, the rod moves away from the magnet. That is the observation you have to remember. Now, why does this rod move away from the magnet? Now, when there is a rod, it is at rest. There is no force acting on it. When there is a force acting on it, it moves. So, where did that force come from? Now, we said there is magnetic field. The current, when we close the switch, current flows through the conductor. Because of that, there is a force generated. Due to the force, the rod moves away from the magnet. So, you have to remember, students, there is a force generated when there is a conductor placed between a magnetic field, and when the current flows through it, there will be a force generated. That is one observation you have to understand. And also, you have to remember, now at this point, when the current flows from A, B, C, D direction and the north and south poles are like this, the rod moved away from the U magnet. Now again I'll place the rod back the same way, but what I'm going to do is I'm going to change the terminals of the battery. We will see whether the rod moves in the same manner or not. So I'm going to change the terminals of the battery. Now here this is positive, this is negative. So current will start from positive terminal, flows through the external circuit. So D, C, B, A. I have not changed the magnet. So the current flow is going to be D, C, B, A. Now let's observe what happens when we close the switch. Now see what happened there. Can you all see what happened there? Again, I'll repeat the procedure. So here you have to remember, students, the current flows from D, C, B, A. You can see the labels here. So when I close the switch, the rod moves and it goes towards the U magnet. Now we change the terminals of the battery. The BC rod goes towards the magnet. So what can you understand from there? There is a force acting on a conductor through which a current flows and the conductor is placed in a magnetic field. And the direction of the force depends on the direction of the current flow. So that is what you can understand from this observation. Direction of the force depends on the direction of the current flow. So that is one part of the activity. Next, what I will do is, I will change the magnet. We will have the south pole on top, the north pole at the bottom, and we will repeat the procedure again. Okay, students. So now the changes I have done, again I have brought the terminals back. This is the positive terminal. This is the negative terminal. So when I close the switch, the current will flow this way, A, B, C, D. A, B, C, D. That is the direction of the current flow. And in the brass rod, current will flow from B to C. But the difference is the south pole, the south end of the magnet is on top and the north end of the magnet is at the bottom. So I have changed the direction of the magnetic field. Current is the same as the first step, but the direction of the magnetic field has been changed. So we will see whether that has an effect on the direction of the force. So now I am going to close the switch. Can you see what happens here? Current flows from A, B, C, D. South is on top, north is at the bottom. The rod moved towards the magnet. Again, we will repeat that procedure. If I close the switch, the rod moves towards the magnet. You all can understand that. So, you can remember, students, the first time I did the activity, the same current flow A, B, C, D, we had the different poles. Now, here south pole is on top, north pole is at the bottom. So, now the rod moved towards the magnet. Earlier, when the north pole was on top and the south pole was at the bottom, the rod moved away from the magnet. So, here you can see the rod moves towards the magnet. I am sure you can understand that. So, from this, what can you all understand, students? Now, from this observation, we have changed the direction of the magnet. So, that means the direction of the magnetic field has changed. And therefore, the direction of the movement changed. So, that means the direction of the force changes. So, from that, you have to understand the direction of the force that is induced due to the current flowing through a conductor placed across a magnetic field depends on the direction of the magnetic field. So, that is the other conclusion we can obtain from this activity. In addition to that, we have already seen that when we change the terminals, when the direction of the current flow changes also, the direction of the movement changes. So, again, I will change the terminals of the battery. So, now here you have to see, students, the positive terminal is here. So, when I close the switch, current will flow from here, D, then C to B in the brass conductor, then B to A, and back to the dry cell. So the direction of the current flow is going to be D, C, B, A. And you have to note that the south end of the magnet is on top, north end of the magnet is below. So now we will see what happens to the conductor, that is this brass conductor CB, when I close the switch. Can you see what happens there? Again, I will repeat it. When I close the switch. So what happens there? The rod moves away from the magnet. So we change the terminals of the batteries. So the direction of the current flow change, the direction of the movement change. So that means the direction of the force that causes the movement depends on the direction of the current flow. So those are the things you have to remember, students. Now we did this activity. Initially you were able to understand that when we place a conductor across a magnetic field and if we pass electricity current through that, there will be a force generated. That is why the rod moves. And this particular force, the direction of the force depends on the direction of the current flow as well as the direction of the magnetic field. So those are the things you all have to understand, students. Okay, students. So did you all observe the activity clearly? I am sure you all did. So you were able to see that when we close the switch and allow the current to flow through the conductor, that is the circuit, the conductor BC moves. And initially, when we had the north pole up and south pole down, and the current was flowing across the conductor in the BC direction, that is ABCD direction, the conductor BC moved out of the magnet or away from the magnet. Then when we changed the terminals of the battery, you saw that the conductor moves into the magnet, towards the magnet. Thereafter, what did I do? I changed the poles of the magnet. South pole up, north pole down. And again, when the current flew from ABCD direction, the conductor BC moved into the magnet. And again, when I changed the terminals of the battery, the BC conductor moved out of the magnet. So from all these observations, I am sure you all were able to understand that there is a force generated due to the current conducting through a conductor placed in a magnetic field. That is why the rod BC, the conductor BC, moves due to the force. And the direction of the force depends on the direction of the current flow and the direction of the magnetic field. And also you were able to understand. Now when we had the poles like this, north and south, the current flow was like this, 90 degrees angle. They are perpendicular to each other. Pole like this, current flow through the conductor was like this, and the movement was either this way or this way. So magnetic field, current flow, perpendicular. The direction of the movement, the direction of the force was also perpendicular. So those were the observations and the understanding you were able to get from the activity. So to write down the observation, I have a table here so that it's easy for us to write. Now here you can see position of the magnet and the direction of the current flow through the conductor BC and the observation. So initially the north pole at the top and the south pole at the bottom. So that means magnetic field is downward. So we have it like that. North to south, the magnetic field is this way. Then the current flows through the conductor BC in the BC direction. That is through the circuit ABCD direction. How did the rod BC move? observation, BC moves out of the magnet. So here BC moves out of the magnet. Or you can say away from the magnet, out of the magnet or away from the magnet. Now here, the second instance, north pole at the top and south pole at the bottom, that is again magnetic field downwards, the same method. But the direction of the current flow through the conductor BC, it's C to B. That means DC BA direction. Is that clear? Then what happens? BC moves into the magnet. Earlier it was out of the magnet, now it is into the magnet. Then what did we do? We changed the poles of the magnet. Here we have south on top, north at the bottom. So the direction of the magnetic field is upwards. South pole at the top and the north pole at the bottom. So magnetic field is upwards. Again, two instances like that, south pole at the top and north pole at the bottom, that is magnetic field upwards. At that instance, initially we had the current flowing through the BC conductor from B to C. That is again the ABCD direction. Then how did the rod move? It again moved into the magnet. You can remember that. BC moves into the magnet. Now this is opposite of the first instance. If I label this as 1, 2, 3 and 4, you can see 1 and 3 are opposite. Why? What is the difference? The direction of the magnetic field. Direction of the current flow are the same, but direction of the magnetic field is different. So the direction of the force is also different. Here the rod moved outwards. The force is outwards. Here the rod moves inwards. So the force is inwards. Again, when we have the south pole up and north pole down, but the direction of the current flow DC BA, C to B. Then BC moves out of the magnet. Out of the magnet. So what can you see there? 2 and 4. Direction of the current flow, same. DCBA, DCBA. But the magnetic field is different. And the movement is opposite. When the north is on top, the BC moves into the magnet. And when the north is at the bottom, BC rod moves out of the magnet. So either way, you can see when we change the direction of the magnetic field, having the current flow in the same direction, there is change in the direction of the force. The same way, when we have the direction of the magnetic field is fixed, but we change the direction of the current flow, then also the rod moves in opposite direction. That means the force is acting in opposite direction. So from all these observations, we can get some conclusions. First one, we can say the rod BC moves due to a force generator. That means a force acts on a conductor placed in a magnetic field when a current is flowing through the conductor or through it. So the rod BC moves due to a force generated. That means a force acts on a conductor placed in a magnetic field when a current is flowing through it. That is the first thing you can understand. That is why there is movement. Then we were able to understand that the direction of the magnetic field direction of the current flow and the direction of the force are all perpendicular to each other. You can say either direction or the plane. Now you can remember when we had the magnetic field acting this way, north to south. Then you saw that the current flow was like that. So we have the magnetic field here. Then we have the current flow perpendicular to that because the magnetic field was acting this way. The conductor BC is across it. So, two different directions. And depending on the current flow, there was this force that was perpendicular. Force is perpendicular to that. But here again, when the current flow is this way, force was in one direction. When the current flow changes, the force was opposite to that. The same way, when we change the north and south poles, there also the direction of the force change. So that is what we need to write after this. So then, the direction of the force depends on the direction of the current flow. This you were able to understand from observations 1 and 2 and observations 3 and 4. In 1 and 2, the north pole was up, so the magnetic field was downwards, but we changed the direction of the current flow. Then in 3 and 4, the magnetic field was up, we changed the direction of the current flow. You were able to see the direction of movement change. And finally, this is also something you were able to see, the direction of the force depends on the direction of the magnetic field. Magnetic field. How did you observe that? Now there are observations one and 3. In 1 and 3, the direction of the current flow is the same, A, B, C, D, but we change the poles of the magnet. And observations 2 and 4. 2 and 4, again the direction of the current flow is the same, DC, BA, but the magnetic field changes. Is that clear, students? So those are the conclusions that you need to get. 4 conclusions. What are the conclusions? The rod BC moves due to a force generated. That means a force acts on a conductor placed in a magnetic field when a current is flowing through it. The first conclusion. Then you were able to see the direction of the magnetic field, direction of the current flow, and the direction of the force are all perpendicular to each other. Is that clear? So that is what I have shown in this. Then the next one. The direction of the force depends on the direction of the current flow. That you were able to understand from the first 2 observations, 1 and 2, where the magnetic field was downwards. Then 3 and 4, where the magnetic field was upwards. And finally, you understood that the direction of the force depends on the direction of the magnetic field. There you have to compare the observations 1 and 3, where we had the current flowing in the same direction. Then observations 2 and 4, again when the direction of the current flow was the same. So these are the observations and conclusions from the activity. So I am sure you all can understand that when there is a conductor placed in a magnetic field and the current is flowing through it, there will be a force acting. And the direction of the force depends on the direction of the magnetic field and the direction of the current flow. So, and that can be explained by the Fleming's left-hand rule. You need to use your left-hand rule to predict the direction of the force. So, that is what we will discuss after this. So, here. A conductor placed in a magnetic field moves when a current flows through the conductor as a result of a force acting on it. So, you have understood that. You can remember, a conductor placed in a magnetic field moves when a current flows through the conductor as a result of a force acting on it. The direction of the force is indicated by the direction of the motion of the conductor. So, this is all what we discussed. You can understand that. The direction of the force is indicated by the direction of the motion of the conductor. And in the activity above, the direction of the magnetic field and the direction of the current through the conductor have been arranged to be perpendicular to each other. That is also what I explained. Direction of the magnetic field and the direction of the current through the conductor have been arranged to be perpendicular to each other. And you will be able to observe that the motion of the conductor takes place in a direction perpendicular to both of the above directions. So that also you understood. Motion of the conductor takes place in a direction perpendicular to both of the above directions. Is that clear? So this is what you understood. So this is the conclusion and the understanding you were able to get from the activity. So you know the direction of the force depends on the direction of the current flow and the direction of the magnetic field. So there I told you all we will learn something called the Fleming's left-hand rule, another rule. Fleming's left-hand rule to predict the direction of the force. So that is something you have to understand. Here you can see, I have already written this. Direction of the force depends on the direction of the magnetic field and direction of current flow. So, here the conclusion says they are all perpendicular to each other. But you saw the rod moving either outwards or inwards. So, that means the direction of the force depends on the direction of the magnetic field and the direction of the current flow. That is what we will be learning using the Fleming's left-hand rule. Fleming's left-hand rule. So, by using the Fleming's left-hand rule, we can find the direction of the force. That is the direction of the movement. I will discuss that a little later, but before that, you all know, students, force is a vector quantity. So, force has a magnitude and a direction. And there are factors that affect the magnitude of the force that is induced. So, that is what I am going to discuss next. The magnitude of the resulting force depends on the following three factors. There are three factors. One factor is the magnitude of the current flowing through the conductor. So, here first one, magnitude of the current. Magnitude of the current flowing through the conductor. Current through the conductor. Then the second one, now we use the magnetic field. If you use a small magnet with a lower magnetic field strength, the amount of force will be less. But once you increase the strength of the magnet, the force also will increase. So, the next factor is the strength of the magnetic field. The magnetic field. Now, we did not do any activity to understand the effect of these factors. We did not change the amount of current flow. We did not change the strength of the magnet. And also there is one more factor, the length of the conductor. Length of the conductor. The length of the conductor. When we have a shorter conductor, the force is less. A longer conductor, the force is more. So, there are three factors: magnitude of the current through the conductor, strength of the magnetic field, and the length of the conductor. You have to understand that when we increase the magnitude of current, when you pass higher current, the force will be greater. Less current, force also less. So, that means when you increase the current flow through the conductor, the magnitude of the force will increase. The same way, when you increase the strength of the magnetic field also, the magnitude of the force will increase. And also, when you increase the length of the conductor, again the magnitude of the force will increase. That means the magnitude of the force is proportional to all three factors. Magnitude of the current through the conductor, strength of the magnetic field, and the length of the conductor. It is directly proportional to all these factors. So, here you can see the force. This is something you need to remember. The force increases as the above three factors are increased, and it decreases when the above three factors are decreased. That is, the force is directly proportional to the three factors given above. So, the force is directly proportional to the magnitude of current, directly proportional to the strength of the magnetic field, and is directly proportional to the length of the conductor. So, by changing these, we can use this particular force in different instances. For example, the motor. In a motor, we have a magnetic field, we supply current to a conductor, and there is a force generated. Because of that force, there is a rotation of the motor. And we can increase the power of this motor by increasing these factors. The strength of the magnetic field, the strength of magnitude of current, and the length of the conductor. I am sure you all can understand that. So with that, students, I will move on to the next slide. So like I said, to find the direction of the force, we will learn this Fleming's left-hand rule. Now before I read everything, I will show that to you all. Now if we take our left hand, you have to use the left hand. Now this was proposed by a scientist called Fleming. That is why we call it as Fleming's left-hand rule. So you have to use your left hand. And in your left hand, you have to use these three fingers. The thumb, index finger and the middle finger. You have to hold them perpendicular to each other. Now here you can see 90 degrees. This is 90 degrees and this also is 90 degrees. So all the three fingers have to be perpendicular to each other. And then, if you look at the three fingers, now here you can see this is how the three fingers should be. This will be the direction of the force. Now you know the current. Direction of the current is indicated by the middle finger. So here you can see electric current, the green color line. Middle finger shows the direction of the current flow. The second finger or the index finger shows the direction of the magnetic field. And the thumb shows the direction of the force. Now here you can see, students, the middle finger or what we call as the second finger. Thumb, first finger, second finger. Second finger points to the direction of the current flow. Then this index finger or the first finger points to the field, that is the magnetic field. And the thumb points to the direction of the force. Just for you all to remember easily, how I remember is when we say second finger, there is a C, so current. First finger, F, field. And when you say thumb, M, motion. Motion is due to the force. So like that also you can remember, but directly you can remember what is indicated by each of the fingers. When you hold them perpendicularly, the middle finger or the second finger is the direction of the current flow. The first finger or the index finger is the direction of the magnetic field, and the thumb is the direction of the force. So we provide the current, we have the magnet, we can predict the direction of the force. Is that clear? So that is what is shown in the diagram. Finding the direction of the force on the conductor based on the directions of the current and the magnetic field. You have to have the three fingers this way. Then, if I read the explanation, Fleming's left-hand rule. Fleming's left-hand rule can be used to find the direction of the force acting on a conductor placed in a magnetic field when a current flows through a conductor. So, this is what we understood using the previous activity. Then, this is the rule. You have to understand the rule. Keep the thumb, index finger and the middle finger of the left hand. thumb, index finger and the middle finger of the left hand perpendicular to one another. And point the middle finger in the direction of the current flow, middle finger in the direction of the current flow, index finger along the direction of the magnetic field. Then the direction pointed by the thumb will be the direction of the force acting on the conductor. So that is what we discussed here. Again, if I read it, keep the thumb, index finger and the middle finger of the left hand perpendicular to one another. And point the middle finger in the direction of the current flow, the index finger in the direction of the magnetic field. Then the direction of the thumb will give you the direction of the force acting on it. Is that clear? So then we will try to understand this Fleming's left hand rule using an activity. So let's go to the lab and do the activity now. Okay students, so as I told you all, I'm going to explain the Fleming's left hand rule using the activity, the setup that we used for the activity before. So now you all know the Fleming's left hand rule. Why do we use it? To find the direction of the force acting on a conductor placed in a magnetic field. So you have to use your left hand, the first three fingers, that is your thumb, first finger and the middle finger, they have to be perpendicular to each other. And you all know the second finger. This finger points to the direction of the current and the first finger or the index finger points to the direction of the magnetic field and the thumb points the direction of the force. So if we know the direction of the current flow and the magnetic field, we can identify the direction of the force. We will try to understand that with the movement of this conductor, that is BC conductor. So you are familiar with this activity students, we did it before also. Now here you can see I have the dry cells here, the positive and the negative terminals are marked. So you all know. From the positive terminal, when I close the switch, current will flow into A. Then when we have the conductor, that is the brass conductor here, BC, A to B, B to C, C to D. And back to the dry cell. That is how the current will flow. So in this part, A, B, C, D will be the direction of the current flow. And during that time, if you look at the conductor here, this brass conductor, current will flow from B to C. At the same time, you can see the magnets. Now the north is on top, south is at the bottom. So the direction of the magnetic field is going to be from top to bottom, north to south. So we can use the Fleming's left hand rule. So field is the index finger, that is going to be from north to south. And the current flow will be from B to C. So it has to be towards y'all. B to C, it will be towards y'all. So what is the direction in which the thumb points? It is this side. So that's going to be from here to here. So we will try to understand that with the observation. Now if I close the switch with the conductor here, now when I close the switch, you saw that the brass conductor moves away from the magnet. So that is what we obtained from the Fleming's left hand rule. Again to observe. Now I'll have the conductor here. The index finger is the direction of the magnetic field. Current is going to flow from B to C by A, B, C, D. So in the conductor, it is going to be from B to C. So if I have the setup this way, you will have to, if you are trying this out students, you have to use your left hand and according to the current flow here, you have to hold the fingers. Then only you will get the correct direction. Now for me, field is downwards, current flow is towards y'all or away from me. So therefore, the motion is this way. So if we try that again, the motion has to be in this direction. Here you can see. the conductor moved away from the magnet. So now, what I will do is, we will change the terminals of the battery and observe what happens. Because you all know here the direction of the force depends on the direction of the current flow and the direction of the magnetic field. So I am going to change the terminals of the battery. So now what will happen? The current will flow from positive to D, then to C, B, A, and back to the dry cells when the switch is closed. So if you apply the left hand rule, Fleming's left hand rule, still the magnetic field is downwards, north to south. So it's going to be down. Now here the conductor, the current will flow from C to D. So that's going to be towards me. If it is towards me, the thumb points in this direction. Thumb points in this direction. So what should happen? If I close the switch, can you all see? I'll repeat it again. I'll repeat this again. Now you can see thumb points towards the magnet. So if we look at the direction, now what will happen? It goes towards the magnet, this direction. So you saw the motion. Again to observe once more. Can you all see? So the magnetic field is downwards. Here the current flow is from C to B, so it's towards me, and the thumb points towards this direction. And the conductor moves towards this direction, towards the magnet. Can you all understand that now? The same way, students, we can change the poles of the magnet and we can do the activity again. So here again, I have the terminals of the battery. This is the positive terminal, so current will flow this way when the switch is closed to A, B, C, D and back to the negative terminal. So here you can see, students, the south end of the magnet is on top, north end of the magnet is at the bottom. So the magnetic field has been changed. So what will happen to the direction of the force? I am sure you all can find it out first. What do? We need to use the Fleming's left hand rule. So the magnetic field is the index finger, that is upwards. Now the current flow is going to be towards y'all. It's going to be from B to C in this direction. So the direction of the force has to be towards the magnet in this direction, direction of the thumb. Let's see whether that happens. So I have the conductor there. Current flow is from B to C towards y'all in this. So when we close the switch, the conductor moves towards the magnet. So according to the Fleming's rule, you have to have the fingers perpendicular to each other. Field is the index finger upwards and the current this way. So the thumb points in that direction. If we observe it with that, here you can see the direction of the movement. It moves towards this side, towards the direction of the thumb. So then, the last change, I will change the terminals of the battery. So now here, this is the positive terminal. So current flows this way, D, C, B, A. D, C, B, A. So in the conductor, the brass conductor, current flow is from C to B. So what will be the direction of the force? Now again, you all know you need to have the fingers perpendicular. The index finger is the direction of the field. So that is upwards, north to south. And the current is going to be towards me. From C to B, it's going to be towards me. So where does the thumb point? Away from the magnet. We will observe that. The conductor moves away from the magnet. So again, to confirm, the field is the index finger. Current is the second finger. So that is from C to B. It has to be this way. And the direction of the motion has to be this way. So can you all see that? That is how we use the Fleming's left hand rule. So you have to remember, students, you have to use your left hand, the thumb, index finger and the middle finger. They have to be perpendicular to each other. The middle finger is the direction of the current flow. First finger or the index finger is the direction of the magnetic field and the thumb points to the direction of the force. Okay, students. So you were able to understand how we can use the Fleming's left hand rule. I used it with the previous activity. So I am sure now you all have a better understanding as to why the BC conductor moved into the magnet or moved away from the magnet. You were able to predict the direction of the force. Is that clear, students? So then I am sure you all can understand what Fleming's left hand rule is. It is used to predict the direction of the force when a current is flowing through a conductor placed in a magnetic field. All three are perpendicular to each other. So with that understanding, students, I will move on to the next slide. Now here we have an exercise. The first question, find and mark the direction of the force acting on the conductor using Fleming's left hand rule in each of the figures given below for the magnetic fields and currents indicated. Now, if you look at this first diagram, the now north and south. So, the magnetic field is in this direction. Index finger or the first finger should point towards the magnetic field. So, magnetic field has to be that way. Now, what is this symbol? Coming out of the paper, a dot with a circle coming out of the paper. So, the second finger or the middle finger is for the current. Current is coming out of the paper. So, what is the direction of the force? Upwards. If you hold it like that, north to south, the index finger points towards the magnetic field, north to south. And the current is coming out of the board. It can be the paper or the board. So, if you are looking at your book, you have to place your hand on the book. So, that means the current is coming out of the page. So, when the current is coming out of the page, the movement will be upwards. So, in the first one, the force acts upwards. Why? Because magnetic field in this direction, current out of the page, therefore the force acts upwards. Is that clear? Then, if you look at the second instance, now can you all predict the direction? I am sure you all can try it on your own. So, once you do that, if I show it to you all, again the magnetic field hasn't changed. So, index finger or the first finger in the direction of the magnetic field. But now you can see this symbol. What does that indicate? That the current is flowing into the board or into the page. So, still I have to have the magnetic field in this direction, north to south. But now you can see the current flows into the board. The middle finger is towards the board, into the board. So, where does the thumb point? It points to the direction downwards. So, the force is acting downwards. Is that clear? So, there. In the second instance, the force acts downwards. Why? Still the magnetic field field is in this direction, but the current into the page or into the board. So that means the direction of the force is downwards. So can you see that here? In this instance, the direction of the magnetic field doesn't change. Magnetic field is always like that, north to south. Current flows this way, the force is upwards. Here we are changing the current flow into the board and the force is downwards. So you can further understand that the direction of the force depends on the direction of the current flow. Is that clear? So then I'll move on to the next slide where we continue with the question. Now here we have two other instances. Now what has changed here? The direction of the magnetic field. Again you use the left hand. You have to have the three fingers perpendicular to each other. Now you can see the north to south, the direction of the magnetic field has changed. So how do you hold it? It has to be this way, north to south. And you can see this symbol, dot and a circle, the current is flowing upwards. So you need to hold your hand this way. North to south, current is flowing out of the board. So where is the force acting? The force is acting downwards. Is that clear? So in this third one, force acts downwards. Why? Magnetic field in this direction and current out of the page. The same way, if you try to understand for the last one, fourth one, again the magnetic field is from north to south. So magnetic field has to be from north to south. Now the current is flowing into the board. Current is flowing into the board. Where does the thumb point? It points upwards. So the force is acting in the upward direction. North to south, current is flowing into the board. Why? The sign is cross with a circle. So the thumb points upwards. So the force acts upwards. So fourth instance, force acts upwards. Why? Magnetic field this way and current into the page. Now here also you can see in both the instances the direction of the magnetic field doesn't change. Always from north to south. The index finger north to south. But the direction of the current flow changes. Because of that, the direction of the magnetic field changes. Now if you compare all four. In the first two, now this is just for you all to understand better. 1 and 2. In the first two instances, you can remember magnetic field was in this direction. When the current was coming out, the direction of the force was what? When you have the magnetic field this way, current this way, then you had the force upwards. So current, this one, force up. When current was going into the page, force down. You all can look at your book and recall what we discussed in the previous one. Here you can remember when the force acts upwards in the first one, where the current is coming out of the page. And when the current is going into the page, force is downward. So that is what I have written here. First and second instances, we have not changed the magnetic field. That is north to south. But the force is up when the current is coming out, and when the current is going in, force is down. Then, if we take the next two instances, what we wrote here, 3 and 4. What happened to the magnetic field? Field changed, opposite direction. Again, we had the instance where the current was coming out. Force was down. Force down. And when we had the current going into the page, the force was up. That is the above one. You can see initially the force was downwards, then the force was upwards. Here you can see force down, force up. Now you all can compare. Now 1 and 2, magnetic field doesn't change, current changes. 3 and 4 again, magnetic field doesn't change, but it's opposite to the previous one, but the current changes. Now if you compare 1 and 3. 1 and 3, what is the difference? In both instances, the direction of the current flow is the same, but the direction of the magnetic field is different. So there the force changes. When the magnetic field is that way, force is up. When the magnetic field is this way, force is down. If you take the instances 2 and 4, again here you can see current is flowing into the page. So when the magnetic field is in this direction and the current is going in, force is up. So from all these, from all the discussions, you can understand even more clearly that the direction of the force depends on the direction of the magnetic field and the direction of the current. So when you change one and keep the other one unchanged, you can understand how the force changes. But when you change both together, sometimes there will be no change in the direction of the force. Here you have magnetic field in one direction, current flowing in a particular direction. Here you have changed both. The direction of the magnetic field is opposite, current is also flowing in the opposite direction. The force is the same. So that is how you need to understand this. As long as you know to use the Fleming's left-hand rule, then it will be easy for you to predict the direction of the force. I am sure you all can understand that. So with that, students, I'll move on to the next slide. So here you can see the action of a force on a current carrying conductor placed in a magnetic field is very useful phenomenon in our daily lives. So like I mentioned one instance, the electric motor. That is very useful. You supply current, you have a magnet, and there is force generated. Because of the force, there is the rotation of the motor. And we use this motor in many different instances. So there, the action of a force on a current carrying conductor placed in a magnetic field is a very useful phenomenon in our daily lives. And some of the instruments constructed based on this phenomenon are given below. Some of the instruments. Now one instrument that I mentioned to you all is the electric motor. motor. Then you are familiar with the voltmeter. Now voltmeter is also something that uses this particular concept. Where you have a magnet, you supply current, there is force. That is how you see the deflection in the voltmeter. The same way, the ammeter. We use the ammeter to measure the current flowing through a conductor. Voltmeter for the potential difference, ammeter to measure the current flow. They are also the same thing. You have a magnet, you have the current flowing through it, there is the force generated, and because of the force, there will be a deflection in the pointer of the ammeter. And also, we measure the reading. How do we get that? You all know the magnitude of current affects the magnitude of the force. Less current, less force. More current, more force. Because the force, the magnitude of the force is proportional, directly proportional to the current flowing through it. So, based on that, you are able to get the reading. Then there is the galvanometer. Now, galvanometer is a center zero galvanometer where you can see the direction of the current flow also. Depending on the direction of the deflection of the pointer, you can identify the direction of the current flow, and also you can measure the amount of current flowing through it. So, in all these, there is the same concept. The phenomenon where a force is generated in a current carrying conductor placed in a magnetic field. So, these are different applications. Electric motor, voltmeter, ammeter, galvanometer. But these two, the voltmeter and the ammeter, they have to be analog ones. They have to be analog meters. If you have the digital meter, then the concept is different. But these are with the analog meters, because you all know the digital multimeters where you measure the potential difference, current and all that, they are digital reading. So, they don't use this particular principle, but the analog ones, they use the same principle. Is that clear? In addition to this, the electric motor, voltmeter, ammeter and galvanometer, there is the loudspeaker. Now, we have used this loudspeaker in one of the previous lessons. I am sure you all know the function also. Why do we use a loudspeaker? To amplify the sound. So that you hear a louder sound. That's why the name loudspeaker. Speaker gives out the sound and the sound is louder. So, there also we use the same phenomenon, where a force is generated due to the current flowing in a conductor placed in a magnetic field. So, I am sure you all can understand all these. So, with that, students, I am going to end this chapter. But as I start the next chapter, I will be discussing how a loudspeaker functions and an electric motor functions. And also, we will discuss in detail the parts of an electric motor and how it functions. So, with that, students, I am going to end this chapter.
To watch these important lessons, subscribe to DP Education's YouTube channel right now. Click on the bell icon to stay updated on the latest lessons. Sri Lanka's largest free online school, DP Education.